for number 103, we have an equation, okay, where we were looking at solving for x, okay, whereupon we have that 1 is equal to negative 2 plus the square root of 2x plus 7 Okay, so we have a single radical term with the square root of 2x plus 7. And if I look at isolating the radical expression, okay, so I can move the 2 over by adding to both sides. Okay, so undoing the presence of negative 2 by adding 2 to both sides, I'm going to have in the rewrite, okay, that 3 is equal to the square root of 2x plus 7. Now, with the nature of the radical consisting of an even root, again, if you think of the principal square root rule, again, the even root of an expression cannot reduce to a constant that is negative. And here we're trying to say that the even root, or in this case the square root of 2x plus 7, ultimately reduces to positive 3. And since 3 is not negative, there is going to be at least one solution for x. So we can proceed. And for what we have with the square root of 2x plus 7, I can undo the radical upon squaring both sides. Okay, so we have 3 squared, again, is equal to the square root of 2x plus 7 which is going to be squared, and again, square root of 2x plus 7. This is where if you were to display the index number, okay, we have the second root of 2x plus 7. And for what we have in this equation at this stage, we have 3 squared is equal to 9. And the square root of 2x plus 7 quantity squared, okay, well that just leads to 2x plus 7. And looking at what we have in solving for x, okay, so you have 9 is equal to 2x plus 7. And isolating the x term upon taking 7 away from both sides, so we have that 9 minus 7 is equal to 2. And we have that 2 is equal to 2x. And with division by 2, we're going to end up with x equal to 1. And with the nature of the radical being an even root, okay, it is recommended that you check. So we have in this equation, now we have 2 times 1 is 2. 2 plus 7 is 9. Now the square root of 9 is equal to positive 3. And we have on the right hand side of the equation, we have negative 2 plus 3, which is positive 1. And that is going to match with what we have originally on the left hand side of the equation. Okay, so x equals 1 is going to check out. Now, for what we have in the case of number 104, okay, and again, we're looking at solving for x in this one. Okay, and here we have 6 is equal to 9 plus the square root of 5 minus 3x. Okay. And just as I had isolated the square root of 2x plus 7, I'm going to do the same thing with the square root of 5 minus 3x. So I'm going to undo the presence of the constant that is right next to it. So I'm going to take care of the 9 by subtracting. And here, upon subtracting 9 on both sides, we have 6 minus 9. Okay, so that is going to be negative 3. And we have is equal to the square root of 5 minus 3x. And again, we have another even root radical. Okay, so again, with the principal square root rule, the even root of an expression cannot reduce to a negative constant. So for what we have in consequence is that because of this -3, and because we're trying to reduce the square root of 5 minus 3x to a negative constant, again, this is going to violate the principal square root rule. And so in this case, there is no solution. Again, the even root of an expression cannot reduce to a negative constant. So 104 again has no solution. And here we're transitioning from solving for x to solving for m. And in this one, okay, so we have for 105, okay, we have that the square root of m plus 18 plus 2 is equal to m. Okay, so m appears twice. Now we have one radical expression with the square root of m plus 18. And sort of like what I did with the square root of 2x plus 7, as well as the square root of 5 minus 3x, I'm going to isolate the square root of m plus 18, that is, get the radical by itself. Okay, in this case, I'm going to take away 2 from both sides. And so, for what we have here, we've got the square root of m plus 18 to the left, and to the right, I'm going to have m minus 2. And undoing the presence of the square root, again, I'm going to square both sides. Okay, now for the square root of m plus 18 squared, or the square root of m plus 18 times itself. Okay, so this will be m plus 18. Now for the square of m minus 2. Okay, just some reminders. Now for the square of m minus 2. I've seen the careless mistake plenty of times where there'll be those who remember to square m as well as -2 or something to that effect. But remember, okay, you're looking at m minus 2 times itself. So you do have the m squared, but you also have to combine outside and inside products, which will be identical with -2m and -2m. So you have a -4m, and -2 times -2 is plus 4. The easy part is remembering the squares of m and -2, but the -4m, they forget about. Okay, so just be careful. So reverting what we have here to our equation. Okay, so you have m plus 18 is equal to m squared minus 4m plus 4. Now we have the establishment of a quadratic equation that is not yet in standard form, but I can set the equation to 0 upon making the adjustments by taking away m and 18. So we're going to have minus m as well as minus 18. So here I'm going to have 0 is equal to m squared, and -4m minus m becomes -5m. 4 minus 18 becomes minus 14. And looking at what we have here upon factoring, so for m squared, This will factor out to m and m. Factors negative 14 with minus 5 sum or difference. Okay, we're going to have plus 2 and minus 7. Again, 2 times negative 7 is minus 14, and 2 plus negative 7 is negative 5. And checking what we're going to have for m and arriving at the apparent solutions. And with the application of the zero product property, if I set m plus 2 is equal to 0, okay, we have possibly that m is equal to negative 2. And with m minus 7 equal to 0, we have the other possible solution for m at 7. So we have 2 possible solutions. Now, it might be that both will check out, or maybe only one will check out, or it might be that we don't have a solution at all. Okay, and so if I check these values, see we have for m equal to negative 2. Now when checking, you don't have to write everything out, but just to kind of show you, again, we had the square root of m plus 18 plus 2 is equal to m. So here with m at negative 2, so I had the square root of negative 2 plus 18 plus 2 is equal to m, which again we have at negative 2. Negative 2 plus 18 is going to be 16. Square root of 16, okay, again, square root of an expression reduces to a non-negative constant. Okay, so just the square root of 16, that will go to 4. So I have 4 plus 2 on the left, negative 2 on the right, and 4 plus 2 is 6. Negative 2 is on the right. So with m at negative 2, we're trying to say that 6 is equal to negative 2, and that's a false statement. So we have in consequence, okay, negative 2 will not check out. So we're not going to have 2 solutions for m. Now, for there to be so much as one solution, we'll have to check out 7 for m. Okay, so going back to our original equation, okay, so we have the square root of m plus 18, so this will be the square root of 7 plus 18. And we have plus 2 is equal to m, which we have at 7. 7 plus 18 is 25. Square root of 25 is 5. And looking at what we have on the left, we have 5 plus 2. That goes to 7. To the right, I already have m at 7. That part is true. So we have consistency with m equal to 7. So that works. So for this equation, we have only one solution, and that is going to be 7. Now, and what we have with 106, okay, we have a similar type of equation, and it seems like perhaps the biggest difference will be solving for the letter n as opposed to m. And for what we have in this problem, okay, so we have but appears to be not that much of a change up from 105. Here we have the square root of 2n plus 29. And we have plus 3 is equal to n. Okay, so not too much of a change. We have a single radical term at the front, followed by a constant is equal to a variable in the same letter we're trying to solve for. So the nature of the problem in 106 is very similar to what we have in 105. And just like before, we're going to isolate the radical, which we have in the form of the square root of 2n plus 29 by subtracting 3 on both sides. So this will leave us with the square root of 2n plus 29. And we have is equal to n minus 3. And once again, looking at squaring both sides. Okay, so the square root of 2n plus 29 squared. So this is just 2n plus 29. As for what we have with the square of n minus 3, okay, so we have n minus 3 times itself. So we have n squared, negative 3n minus 3n becomes negative 6n plus 9. So you have another trinomial. Okay, so we have, going back to our equation, so we have another quadratic. And just putting what we have in standard form. So we're going to deduct both 2n and 29 so as to set the equation to 0. Okay, so we have that 0 is equal to n squared minus 8n minus 20 upon factoring. Okay, so you're going to have, looks like n plus 2 times n minus 10. So 2 times negative 10 is negative 20. 2 plus negative 10 is negative 8. And utilizing the zero product property. So for n plus 2 is equal to 0, we have that n is equal to negative 2. For n minus 10 equal to 0, okay, so you have that n is equal to 10. And again, just sort of checking the results here. Again, you can just do it visually. Without necessarily having to write. So we have it n at negative 2. So the square root of 2 times negative 2 plus 29. Followed by the addition of 3 is equal to negative 2. So you got negative 4 plus 29, so this will be 25. Now the square root of 25 becomes 5, not negative 5, 5 only. Alright, so combining, on the left we have 5 plus 3, which is 8. And to the right I have n at negative 2. So plugging in n equal to negative 2, I'm trying to say ultimately that 8 is equal to negative 2. When it is not, so negative 2 is going to strike out. And for n equal to 10, so you have the square root of 2 times 10 plus 29, followed by the addition of 3 is equal to 10. We got 2 times 10 is 20 plus 29 is the square root of 49. Again, square root of 49 is 7 and only 7. And we have 7 plus 3, which is going to be 10. And we have 10 is equal to 10. Okay, so that is going to be true. So where n equals 2 comes up short upon examination, 10 works out as the solution. And so for 106, there is only one solution for n, and that is going to be at 10. Okay. Now, in looking at what we have with the next items. Okay, now again, with even root radicals, okay, there is the preoccupation with the principal square root rule. Again, just reminding ourselves that the even root of an expression cannot reduce to a negative constant. But in the case of odd roots, you're not going to have that preoccupation, okay, because the principal square root rule does not apply to odd roots. For you can take the odd root of an expression and have it to go to a positive or even a negative constant, or even 0 for that matter. Now for number 107, okay, we have negative 4 times the cubic root of 2x minus 5, followed by the addition of 6, is equal to 10. Okay, and again we can isolate the cubic root of 2x minus 5. Okay, and we can start out, okay, one possibility is to go ahead and take 6 away from both sides. So we're going to have negative 4 times the cubic root of 2x minus 5 is equal to 4. Okay. And in this one, okay, so I can get the cubic root expression by itself if I divide by negative 4. 4 over negative 4 goes to negative 1. Negative 1 is an integer. And some of you might be wondering, just like the other day, could I keep what I have here and cube both sides? And the answer to that question is yes. You would have some very high absolute values among the coefficients, but you could cube both sides and solve for x that way. But we'll just divide by negative 4. Because division by negative 4, it's not going to lead to a fraction. We're just sticking with integers in this one. So if I divide by negative 4, okay, so left-hand side, so we have the cubic root of 2x minus 5, and we have equal to 4 over negative 4, which will be negative 1. Again, if I had this set up as like the second root or fourth root or any other even root of 2x minus 5 equal to negative 1, automatically there would be no solution. But since I'm dealing with an odd root, in this case, I can continue. So I have the cubic root of 2x minus 5. I'll raise to the third power. Okay, and I have equal to negative 1 also raised to the third power. So the left-hand side we're going to have at 2x minus 5. Negative 1 to the third is going to be still negative 1. And in the follow-through, I'm looking at solving for x. So I can isolate 2x upon adding 5 to both ends. So we're going to have 2x is equal to 4. And with division by 2, okay, we have our solution at x is equal to 2. Okay. So again, we had an odd roots radical to deal with. Now if I had an even root, you'll be looking at checking as a recommendation. Okay. Now for 108, I have another odd root expression, and this time we have in the fifth root, and this time we have negative 3 times, okay, the fifth root of 4x minus 1. We have followed by the addition of 2 is equal to 8. And if we isolate the radical, so taking 2 away from both sides, so we'll have negative 3 times the fifth root of 4x minus 1 is equal to 6. Now let's go ahead and divide by -3. And doing so we have the fifth root of 4x minus 1 is equal to, and 6 divided by -3 is going to be -2. Okay, so to free up 4x minus 1, okay, we'll take both sides and now raise to the 5th power. Can I have equal to -2 to the 5th? Okay, so we have 4x minus 1 equal to, and for -2 to the 5th, so looking at going from -2 to 4 to -8 to 16, and 16 times -2 is going to be a -32. And so we have with 4x minus 1 equal to -32. So adding 1 to both sides, and we'll have 4x equal to -31. And for the solution in x, okay, this is just going to be a negative fraction, where we have x equal to -31/4. All right. Now, for what we have in the case of 109, okay. Now this one, this is quite a problem here, and I think there might be one in the ALEKS set where we have 2 radical equations involved. Okay. And for 109, now we're looking at solving for the variable p, whereupon we have the square root of 8 minus p minus the square root of p plus 5 is equal to 1. Okay. So notice we have not one radical expression like we have had throughout the examples and problems we have encountered so far, but 2. And what you can do here is to isolate either of these 2 radicals and just move the other. And say what if we just leave the square root of 8 minus p by itself on the left, I can just move the square root of p plus 5 over by adding. And upon doing so, I have the square root of 8 minus p and we have is equal to 1 plus the square root of p plus 5. And I can free up the 8 minus p upon squaring both sides of the equation. Okay, so we have the left-hand side at 8 minus p. Now, for what we have to the right, okay, so I have 1 plus the square root of p plus 5 squared so I have 1 plus the square root of p plus 5 times itself. Okay, so if I FOIL out, so got the first product we have at 1, outside product we have 1 times, okay, the square root of p plus 5. And inside product had the square root of p plus 5 times 1. So you have another square root of p plus 5. And we have with the last set here, we have the square root of p plus 5 times itself. So combining, we have 1. For the radical terms in the middle, so you have like 1 square root of p plus 5 plus 1 square root of p plus 5. So this will become 2 times the square root of p plus 5. And then for the square root of p plus 5 times itself, you have plus p plus 5. And we have in the arrangement, now we have 1 and 5. We have constants to combine. Okay, so the right hand side of the equation, okay, so we have with 6 plus 2 times, okay, the square root of p plus 5 plus p and looking at what we have, again, we still have a bit of a radical remnant, okay, with 2 times the square root of p plus 5, and I'm going to get that term by itself. Okay, so I'm going to move the 6 over by subtracting, and also the p from the right. Okay, so we're going to have 8 minus 6. Okay, so this will be 2. We have minus 2p. It's equal to 2 times, okay, the square root of p plus 5. So if you notice, we have 2 minus 2p is equal to 2 times, okay, the square root of p plus 5. And what I can do here, notice you have 2 negative 2p, 2 times the square root of p plus 5. So I can go ahead and just kind of clean things up, just dividing the equation by 2. Okay, so if I divide the equation by 2, so left hand side of the equation, okay, so that is going to be 1 minus p. Right hand side is going to be the square root of p plus 5. Okay, now with the square root of p plus 5 by itself, okay, so again, we have the next phase, okay, we're looking at squaring both sides. Okay, just sort of mention, so you have with 1 minus p squared. Okay, so I have the quantity 1 minus p times itself. In the FOIL, okay, now I have 1 minus p and another minus p. Negative p times negative p is going to be p squared. So we're going to have 1 minus 2p plus p squared. And it really doesn't matter what order you place this, but I'm going to go ahead and put the highest degree term at the front. So you have p squared, just put that at the front, have minus 2p in the middle, and just shift the 1 over, have plus 1 at the end. Okay, so in the rewrite, so we have p squared minus 2p plus 1. is equal to, and the square of the square root of p plus 5. So this will go to p plus 5. Now we have a quadratic equation that is not yet in standard form, okay, but I can make the adjustments here by taking both p and 5 away from both sides. Okay, so we have p squared minus 3p minus 4 is equal to 0. And in factoring, okay, so we'll have for p squared minus 3p minus 4, can we have as one factor, we have p minus 4, and the other we're going to have with p plus 1 okay, so we have with p minus 4 equal to 0, we're going to have one apparent solution with p at 4, and with p plus 1 equal to 0, we have that p is equal to negative 1. And just looking at what we have in the setup, and just sort of expanding the view here. There we go. So just as kind of a quick check, if I were to check out p equal to 4, okay, you have 8 minus 4, you have the square root of 4, and okay, 4 plus 5 is going to be 9. Okay, so 8 minus 4 is 4. Now the square root of 4 is going to be 2. And you have minus. Now 4 plus 5 is 9. Square root of 9 becomes 3. Now the right hand side we have fixed at 1. And guess what? 2 minus 3 is negative 1. And that's a false statement. So saying that p equals 4 is a solution is trying to say that upon putting back, again, it's trying to say that negative 1 is equal to 1, in which it is not. So 4 is going to strike out. And there's only one possibility left over for not x, but for p. And that's going to be with negative 1. Okay, so you have 8 minus negative 1, which would be 8 plus 1, so this will go to 9. Negative 1 plus 5 is 4. Again, we have the equation set equal to 1. Now the square root of 9 is going to be 3. You have minus. Now the square root of 4 is 2. 3 minus 2 is 1. And 1 is equal to 1. So that is a true statement. So where 4 came up short, okay, we have consistency to come about whenever we set p equal to negative 1. So negative 1 checks out. So it's going to turn out that for this equation, there's only one solution, and that is for p equals negative 1. Okay, and we will look into 110, but for right now, I want to make a bit of a transition to what we have with absolute value equations. Okay, and for what we have with absolute value, okay, so we're going to throw in some symbolism here. Okay, so we have with okay, just symbolically. Okay, so the absolute value of x, okay, we have denoted by what would be vertical bars surrounding the letter x. And by definition, okay, so the absolute value of x for the absolute value of x, okay, this is going to be the number of integral steps that x is away from 0 on a number line. And in the case of absolute value, absolute value is going to be a non-negative quantity. And just in the case of examples of absolute value, you have something like the absolute value of 14 is equal to 14. Absolute value of a positive number is going to be a positive number. And likewise, the absolute value of a negative number. They have like that of negative 37. Absolute value of negative 37 is going to be 37. So you're still saying like negative 37 is 37 steps away from 0, but it'd be on the other side. And in the case of absolute value of 0, well, you're not moving away from 0, increasing or decreasing. So absolute value of 0 is 0. Now for what we have regarding absolute value equations, okay, so just going from absolute value itself to absolute value equations. So if we have that, if k is a non-negative value, okay, so that means that k is greater than or equal to 0. That is, k could be equal to 0, or it could be a positive number, whether it's like a positive fraction, like positive 4/5, or a whole number, like positive 3, or an irrational number, like, say, pi. And say that if k is a non-negative value, and we have that the absolute value of x is equal to k, say if k is a non-negative value and the absolute value of x is equal to k, then you're going to have that x, once you take x out of the absolute value bars, that's going to be equal to plus or minus k. We have that x could be k or negative k. Right. Now let's say that in the case of absolute value equations, Okay, so if we're looking at solving for x, and just kind of get squared away here. Say if we have the absolute value of x is equal to 7. All right, so we're looking at solving for x, okay, and so we're looking at determining those numbers that will have an absolute value of 7. So here k is represented by 7. 7 is not negative, okay, so there will be solutions in x. And again, those numbers will be 7 units away from 0. They're going to have 7 itself and also negative 7. So x is equal to plus or minus 7. So those would be our possible solutions in x. And if we have something like an expression, okay, say we have the absolute value of 2x minus 7 followed by the addition of 2 is equal to 19. Okay, so we have the absolute value of 2x minus 7 plus 2 is equal to 19. So you don't have yet the one-to-one lineup between the absolute value of the expression and the constant k right yet, because we had that plus 2 that's creating a bit of an obstacle. But we can just move the 2 over. And in the rewrite, so we're going to have the absolute value of 2x minus 7 is equal to 17. Okay. And we have a one-to-one correspondence between the absolute value of an expression on one side and the constant on the other. So you have x represented by 2x minus 7, k is represented by 17. And if I take out the absolute value notation, we're going to have two pathways for 2x minus 7. And it'll be equal to those numbers that will be 17 units away from 0 on the number line. So one is going to be positive 17 and the other negative 17. And finding out what values of x will set 2x minus 7 equal to positive and negative 7. Yeah, 2x minus 7 equal to positive or negative 17. So you have for 2x minus 7 equal to negative 17. And for 2x minus 7 equal to positive 17. So if I isolate the x term for both equations, so I can add 7 to both ends. At the lower end, okay, we have 2x equal to negative 17 plus 7, so we have a negative 10. And if I divide by 2, so we have that x is equal to negative 5. Now for 2x minus 7 equal to 17, if I add 7 to both sides, so we have 2x is equal to 24, and we have a division by 2, okay, we'll come out to x equal to 12. So x will have two solutions. At the lower end we have at negative 5, and the other, okay, we're going to have at positive 12. And let's say that if we have another case here, and we'll say we have that the absolute value of x plus 5 is equal to negative 16. So yeah, the absolute value of x plus 5 is equal to negative 16. Now we have one-to-one correspondence. We have the absolute value of x represented by x, and k is represented by negative 16. But again, stressing the non-negativity part. Absolute value is a non-negative quantity, and k is supposed to be a non-negative value. So just Okay, taking what we have here, whatever we have the absolute value expression set equal to, the constant cannot be negative. So we have, in consequence, there will be no solution. Now, that's a little bit of an added case, and this is same nature in the type of problem, but just a little added dimension in terms of the problem solving treatment and how to go about isolating the absolute value expression. Say we have negative 3 times the absolute value of 2x plus 6. We have plus 6 is equal to negative 24. Okay, so this is the first case where we have explicitly a coefficient in front of the absolute value notation. And what you're going to do here is that you're going to treat the absolute value of 2x plus 6 differently from where you would have 2x plus 6 in parentheses. Okay, so you're not going to distribute so in other words, do not treat the absolute value of 2x plus 6 as you would if you had 2x plus 6 in parentheses. So in other words, we cannot take direct distribution and say we have negative 6x minus 18. So you're going to have to work around, okay, the absolute value symbols, okay, with the outside coefficients. So for what we have in this setup, okay, so just like what we did with the earlier case, I had addition of 2. Here I have the addition of 6. So I can just remove that constant by subtracting. And so we're going to have, in the rewrite, okay, we will have negative 3 times the absolute value of 2x plus 6. And we have is equal to negative 24 minus 6. Now negative 24 and negative 6, okay, this will be at negative 30. And again, I cannot distribute negative 3 over 2x plus 6. Now you might have a solution, but it might deny you of a second solution. So in terms of what to do with the negative 3, I'm just going to divide on both sides. Alright, so with division by negative 3, okay, so left-hand side, we have the absolute value of 2x plus 6. And to the right, have negative 30 over negative 3, so this will be a positive 10. Okay, so finally, it took quite a few operations to get it to the format of the absolute value of x is equal to k. Now the k value is going to be at 10, and as I remove the absolute value of bars, so we have 2x plus 6 is equal to the numbers that will have a distance of 10 units away from 0. Okay, one at 10 and the other we have at minus 10. And looking at solving for x, okay, so setting up our equations. So you have 2x plus 6 is equal to negative 10, or it could be that 2x plus 6 is equal to positive 10. And we have with the simultaneous equations. So if I isolate the x term by taking 6 away from both sides, so you have 2x is equal to, and negative 10 minus 6 is going to be negative 16, division by 2, so this will lead to x is equal to -8. And taking 6 away from both sides in the second equation, so we're going to have that 2x is equal to 4. And with division by 2, so we have that x is equal to 2. And so we have for x, there will be two solutions again, one negative and the other positive, which we have a -8 and 2. All right, and let's say that for what we have in working with absolute value. And tell you what, let's see what we get. So we have solving for x. Okay, so we'll say that we have that the absolute value of x is equal to 15. And we'll say that we have the absolute value of 2x is equal to 22. And we'll say we have the absolute value of x minus 22 is equal to -10. And we'll say that we have as a fourth case, and we'll say that we have -4 times the absolute value of 3x minus 2 plus 10 is equal to -54. Okay, so for the next few moments, let's see what we get for x among these four absolute value equations. Okay, for what we have among these four problems, we're looking at seeing if we have any solutions for x, and if there are, we're to identify them. Okay, so we have at the start, okay, so we have first items, okay, we have the absolute value of x is equal to 15, okay, and so we have k represented by 15, which is a non-negative number, and so we are going to have solutions for x, and so if k is at 15, then x is equal to plus or minus k, so we have those numbers that will be 15 units away from 0, and those numbers will be positive and negative 15. Okay, for the second item, okay, so we have that the absolute value of 2x is equal to 22. Okay, so as take care of the absolute value bars. Okay, so we have going from absolute value of 2x to 2x. Again, 2x is going to be 22 units away from 0 on the number line. And values that are 22 units away from 0, we have 22 as well as -22. So looking at the values of x, that will ensure that 2 times x is going to be 22 units away from 0. And we have for the possible values, we have at the lower ends, we have 2x is equal to -22. And at the upper end, we have that 2x is equal to 22. So we're going to end up with additive inverse values. Okay, so we have x is at -11 whenever 2x is equal to -22. And for 2x equal to 22, we have that x is equal to 11. So just going back, 2 times -11 is -22. And the absolute value of -22 is 22. And again, 2 times 11 is 22. And the absolute value of 22 is 22. So we have, in this order, we have another set of additive inverse solutions with negative and positive 11. Now, for what we have in the third item, we have that the absolute value of x minus 22 is equal to minus 10. Okay, and for what we have here, okay, we have the absolute value of x represented by that of x minus 22, and k we have represented by negative 10. However, k is supposed to be a non-negative value, and since we have k on display as being at negative 10, if we had a positive 10 instead, we would have had sets of values for x in the solution. But here, because of the negative sign, we cannot have that which represents k to be negative, so we have no solution. Now, for what we have in the fourth item, okay, so we have an absolute value equation, and here we have, again, in terms of getting the absolute value of 3x minus 2 by itself, here we have a couple of obstacles to remove. One is going to be 10, which is added, and so we're going to subtract. So we have in the rewrite, so we have negative 4 times the absolute value of 3x minus 2 is equal to negative 54 minus 10, so this will be a negative 64. And again, taking care of the coefficient negative 4, which will be done not by distribution, but by division. Okay, and so with what we have here, okay, we have the reduction down to the absolute value of 3x minus 2 is equal to, and for negative 64 divided by negative 4, this will be a positive 16. Okay, so k is at 16, absolute value of x is symbolized by the absolute value of 3x minus 2, and upon dropping the absolute value bars, so we have 3x minus 2 set equal to those amounts that will have an integral distance of 16 units away from 0. And so those numbers have at positive and negative 16. So in setting 3x minus 2 to negative 16 as well as 16, and we're going to have in the setup, so adding 2 throughout on both sides of both equations. So we're going to have 3x is equal to negative 14. And also we have 3x is equal to 18. So for what we're going to have at the lower end, with division by 3, so we have negative 14 thirds. And with the same follow through for what we have at the upper end, we're going to have the x is equal to 6. Okay, so for the solution sets, okay, we have a negative and a positive value, respectively, with minus 14 thirds and positive 6. All right, and just a remaining item. Okay, now again, we're going to be looking at equations that will consist of non-integer exponents. And I tell you what, I'm going to sort of save that one. And I said that we will be looking into that number 110, and that was the other problem that had two radical terms in the mix. And this one is also a bit of a doozy. Okay, so we have in this problem, so we're looking at solving for the variable d. And this time we have the square root of d plus 4. And we have minus, okay, the square root of 6 plus 2d is equal to negative 1. Okay, so we've got a difference of radical terms. Both of these are expressed in terms of square roots, and we can isolate either one of these radicals. So I'm going to get the square root of d plus 4 by itself. So I'm just going to move this square root of 6 plus 2d over. Alright, so to the left, okay, so I'm going to have just the square root of d plus 4. Again, we have equal to negative 1 plus the square root of 6 plus 2d. Okay, and for what we're going to have in the setup, now we're going to square both sides. There we go. Okay, so for what we have on the left, okay, so this will be d plus 4 right away. Okay, now for negative 1 plus the square root of 6 plus 2d squared, I'm just going to mention, so you're going to have, so this would translate out to negative 1 plus the square root of 6 plus 2d times itself. And if I take the FOIL, now we got negative 1 times negative 1. This will be a positive 1. Outside product, we have negative 1 times the square root of 6 plus 2d. So you have a minus square root of 6 plus 2d. That's why the inside product had the square root of 6 plus 2d times negative 1. So we have another subtraction of the square root of 6 plus 2d. Now for the last, you're looking at the square root of 6 plus 2d times itself. Or in this case, we had the square root of 6 plus 2d squared. And in the follow through, okay, so we have 1. Now we have back to back, think of like negative 1 square root of 6 plus 2d, and another negative 1 times the square root of 6 plus 2d. So back to back we'll have a negative 2 times the square root of 6 plus 2d. And then we have at the ends, okay, we have 6 and 2d to be freed up. And just combining, so we have 1 plus 6 is 7. And you have minus 2 times, okay, the square root of 6 plus 2d. And you got that 2d that is left over. Okay, so we're going to have 7 minus 2 times the square root of 6 plus 2d. Plus 2d. Okay, so for what we're going to have in the setup, okay, now if you notice, okay, we have that radical remnant left over, and what I'm going to do here is that I'm going to isolate this term, And first of all, I'm just going to move the 7 and the 2D over. Okay. So we have in the case of moving. It's got minus 2D. You have minus 7. Okay, so you have D minus 2D, so this is going to become negative D. 4 minus 7 is going to be at negative 3. And we have negative 2 times the square root. Okay, we have 6 plus 2D. And what we can do here is that if you notice, you have all these terms are negatives. So I'm just going to multiply this whole equation by negative 1. So just changing signs. That is multiplying or dividing by negative 1. So D plus 3 is equal to 2 times the square root of 6 plus 2D. Alright. And if you notice, we have odd coefficients on the left with 1 for 1D and 3, but you have an even leading coefficient with 2. And if you want to sidestep from having to deal with fractions, you can just go ahead and square out, okay, what we have present. Okay, now remember, D plus 3 squared is going to be D plus 3 times D plus 3. So easy part is the D squared and the last part. But remember, you got 3D plus 3D, which would be 6D. And 3 squared is going to be at 9. And then for what we have next now, 2 squared is 4. Square root of 6 plus 2D squared is going to be 6 plus 2D. Now remember, we still have multiplication to perform. So again, squaring the factors does not automatically take care of the multiplication. So here we have 4 over 6 is 24. And 4 over 2D, so this will become 8D. And if I rewrite this equation in standard form, okay, so I'm going to take both 8D and 24 away from both sides. So we have D squared minus 2D minus 15 is equal to 0. And then factoring, we have D plus 3 and D minus 5. And for the zero product property, okay, so if I set D plus 3 to 0 and D minus 5 equal to 0, now there will be two apparent solutions with negative 3 and 5. Now it might be that both will check out, or that one will check out, or that none will check out. And just looking at what we have now with negative 3 and 5. See if I can get this view just small enough. Yeah. So you have a D at negative 3, going back to what we have here. So if I check D equal to negative 3, now negative 3 plus 4 is 1. And 6 plus 2 times negative 3. Okay, so that's going to be the square root of 1 minus the square root of 0 equals negative 1. And square root of 1 is 1. Square root of 0 is 0. So in putting back with D at negative 3, we're trying to say that 1 is equal to negative 1. So this part here, okay, does not quite work out. But now for D equal to 5. Okay, so you got 5 plus 4 is 9. For the next radical, okay, so you have minus the square root. 2 times 5 is 10 plus 6 is 16. Okay, so you have square root of 9 is 3. Square root of 16 is 4. 3 minus 4 is negative 1. And we have left hand side is negative 1. Right hand side is likewise. So both sides agree. So, and that possibility is created by setting D equal to 5. So we have in this one, okay, between the apparent solutions that we have for D, only 5 is going to check out. So for this problem, there's only one value that works for this difference of radical